Hi guys, in this video I'm going to discuss about Atcoder beginner contest 409 problem E. So the problem is called pair annihilation. So you're given a tree with n vertices. The vertices are numbered 1, 2 until n, and the edges are numbered 1, 2 until n minus 1. And Hj bidirectionally connects vertices Uj and Vj, and it has a weight Wj. So it's a weighted graph. And also, vertex I is given an integer xi. If xi is more than 0, then it is filled with positrons, else it is filled with electrons. And if xi is 0, then nothing is placed at vertex I. Here it is guaranteed that the sum of all positrons and electrons are 0. Okay, so moving one positron or electron along the edge costs the energy W, so it will cost the weight. And when a positron and an electron meet, they will annihilate each other in equal numbers. So let's see the test cases here. So I'm going to pick the sample input number 3 to show you how it's done. Okay, so let me test my notes first. Alright, okay, so the first idea is that you need DFS. Okay, I usually use DFS instead of like BFS in the tree. Usually they're the same, but I prefer DFS because it's simpler. Okay, so first of all, we need DFS, and second of all, we need to think greedily. So it's greedy. So let's say, you have this kind of tree, right? And you want to destroy like, so you have +1 and -1 here. So you can actually make both of them meet at the root instead of like, let's say I have +1 here, right? Then later -1 here, then the +1 goes here. Technically they're the same, but this idea is much simpler, and in fact I will build upon this. Okay, so the way that we can do this is that, first of all, okay, maybe I should just choose this first. Okay, I will draw this first. Okay, so 1 is 3. Okay, so I will draw the tree first before switching to another screen. Okay, maybe I should just make it something like this. Okay, 1 3 5 2 4. Okay, so the tree will be something like this. Okay, so I'll just label the root here. Okay, so as you can see here, so 2 5 has weight 0, and then we have 8 here. So we have 8 here, sorry, -8. Then we have 0 here. Then of course we cannot do anything here to remove the -8, so it needs to go up. So if it goes up, right, oops, sorry, I show you my solution. I should show you later. Okay, so yeah, it goes up, and then we have 5. Okay, 5 is 2, so 2 here. So technically, when oops, I keep sorry, I keep pressing that. Okay, so we have -8, we go up, and then we have 2. So technically this thing will be -6 later, because -8 plus 2. So the idea is simply like this. Okay, let me erase this. Okay, so let's say we have in 3, right? So we are in 3. We need to find the size of this subtree. Size of subtree. Okay, size of subtree, and then we add. So we multiply by this, by W. So the weight of this edge. So we have W, then we have the size of the subtree. So what's the size of the subtree? It's actually positron plus electron. Yeah. Okay, so later we need to do the same here also. Then we add to the answer. So answer plus, yeah. Then we just go up more and more until we reach the root. Okay, so this is my solution. So I input like usual, and then I put the adjacency list as usual, and I have the subtree size. So I will store the subtree size, and then later I will make like size, and then later we check if the size of the adjacency list is equal to 1 and the node is not 1. So I want to detect a leaf, so like this, like 2 and 4 in here. But let's say there's a case like 1 2 3 4. Technically here, right, if I don't mark 1 as root, it will detect 1 as leaf. So we need to somehow mark this. Oops. Cannot write. Oops. Mark. Yeah. Okay, so we need to mark. Then later we just find the size of the subtree as usual. Then later we find the size of the subtree here, the size of the subtree of the child, and then we multiply by the weight of the edge that connects the node and the subtree. Then later we just print the answer. Okay, so I think that's all for this video. I'm going to discuss the rest of the problem set in another video. Okay, thank you.